Hi everyone, my name is Debanjan. I am a third year PhD student at ICTS. I would like to begin by thanking the organizers for this nice opportunity to talk about my work here. So, in this talk, I will briefly summarize the work I have done with this set of people. Two of them are PhD students, and one of them is a faculty member at IIT Kanpur in the Department of Physics. So, as the title suggests, I'm going to talk about some cutting rules for cosmological correlators. So, let's start. So, cosmology is the most glorious of all the historical sciences, as Nima says, and it is glorious because it is very ambitious in answering the type of question it is supposed to answer. For example, what created our universe, what created everything that we get to see around ourselves, and so on. And as we all know, during the creation of the universe, the energy scale was so high that it might be able to lead to the theory of quantum gravity. Therefore, the motivation in cosmology is really ambitious. Okay. However, there is a difference between the type of experiments that we talk about in the particle physics and in cosmology. In the particle physics, we can think of colliding particles and let them disperse, and then measure something called scattering amplitudes, and from there we can compute the observables of the scattering cross sections that we can really measure using the LHC. However, in cosmology, the nature does its own experiment. Therefore, we can't get to go and set up some initial conditions and do the experiments. Therefore, what we are doing is we are observing the imprints of the experiments that was left somewhere, as for example, in CMB or in LSS. Okay, so but just by looking at them, we know like there are some initial very tiny quantum fluctuations which were stretched to the cosmic scale that gave rise to this large scale structure. Okay, and in cosmology, the type of observables people think of are just the spatial correlations at the very late time of the universe. So they are in principle some in type correlators. You can think of some averages. So these are called the cosmological correlators. And so far, people have been able to measure the 2-point correlator of scalar perturbations. However, one of the goals of recent time is to measure higher point correlators and the tensor perturbations. However, in computing the higher point correlators, it becomes quite technical and challenging. Therefore, the goal is to look for some ways, some innovative ways, so that we can compute the higher point correlator in terms of the lower point correlators and so on. Okay, so this is going to be roughly the idea of today's talk. Therefore, and if you remember, like as I just said, like it's a historical science. Therefore, there is some imprint of time. Likewise, in our particle physics, like the unitary evolution of time has imprint on the scattering amplitudes in terms of the so-called optical theorem, which further leads to cutting rules and which enables us to compute some higher order amplitude in terms of the specific combinations of the lower order ones. So higher and lower order, I mean the at the higher and lower order of the coupling of theory. So in the stuff, what we are going to look for is if there is some analogous statement in the cosmological correlator as well. In the cosmological correlator, can we also construct the higher point correlator in terms of some lower point objects? It might be correlator or it might be something else that we are going to see. Okay. And let me also mention that in the last few years, there has been significant progress in the understanding of this or above questions, which is the imprint of time in the cosmological observables and so on. Okay, so before going into the details, let me set up the stage so that I can refer to some of the standard notations and so on. So a cosmological background is well approximated by the expanding Poincare patch of a 3 plus 1 dimensional de Sitter spacetime. And there are two primitive ways of computing cosmological correlators. However, recently there are many. For example, in-out formalism devised by Enrico and his collaborator, and also the bootstrap technique devised by Daniel Baumann and his collaborators, and so on. But the two primitive methods are the wave function approach and the Schwinger Keldysh formalism, also known as the in approach. So, in the wave function approach, people define something called the wave functional, which is given in equation 1, and this in the right hand side, the psi n prime are called the wave function coefficients. However, throughout the talk, I will suppress this prime. It just means that whenever you are writing psi n prime delta q, and the difference between psi n and psi n prime is just the factor of the three momenta conserving delta function. However, in my talk, I will always use psi n instead of psi n prime. Okay, and from the given wave functional, if you want to compute the correlator, you take the mod chi square and solve this derivative, solve this integrations, and you land to the cosmological correlators. And in each field in the cosmology, each field in the momentum space can be written in terms of the creation and annihilation operator with their corresponding modes. So fk plus is the creation modes, and fk minus is the complex conjugate of the fk plus, and which is the annihilation mode. Okay, and fk plus can actually be from the Klein-Gordon equation. One can show that fk plus can take this formula. H nu 2 is the Hankel function of type 2, and nu is given by this formula. In throughout the talk, I will mostly focus on something called conformally coupled scalar, which has m is equal to root 2 by h, which leads to nu is equal to half. And for m is equal to 0, it is called massless scalar field theory, for which nu is equal to 3 by 2. And for this particular choices of nu, the Hankel function really has very simpler form. Okay, and all the wave function coefficients and the correlators can be computed using the Witten diagrams in the momentum space and so on. So what do you already know about this imprint of time on the cosmological correlators? So, so the first thing that I'm going to discuss is this optical theorem for this wave function coefficient derived by Goodhue, Sadra, and Payer, where they showed that the unitarity and analyticity conditions together gives this set of this kind of formula that's written in equation 4. So here you can think it of as there is an wave function coefficient, it's psi 4. So psi 4 is a 3-level exchange wave function coefficients. So ki are all the external line, and as is the bulk to bulk exchange line. So its as is actually mod of k1 plus k2, if you like. Therefore, this combination can be written in terms of some lower point wave function coefficient, which is psi 3. So here the interaction that they chose was phi phi sigma. Phi can be conformally coupled or massless scalars, and here sigma is just the heavy fields. Okay. So the in terms of diagram, if you want to think of, you take a psi 4 and do some operation. Let's say it's something called the discontinuity operation. So whenever you are applying this discontinuity operation, you can think it of drawing a cut lines. And whenever you have a cut line, so take that cut line, join it to the boundary, and then think of the two different parts, which now has three bulk to boundary lines, phi, phi, and sigma. So these are really the psi 3, the contact level wave function coefficient, which is at the linear order in the coupling constant. However, on the left hand side, you see it's the quadratic order in the coupling constant. So therefore, you can really show that the higher point wave function coefficients are related to the lower point wave function coefficient in this way. So later on, Melville and Payer also developed something called the cutting rules, which actually works for even at the loop order and so on. So which is in equation 5. So sub-diagram are really at the lower order in the coupling constant. However, on the left-hand side, the actual diagram could be at any higher order in the coupling constant. Okay. And later in Goodhue, in a paper by Goodhue, Sadra, Gordon Lee, and Paye, they came up with something called the single cut rule. And in that rule, they showed that if you take the discontinuity of an higher point wave function coefficient, it can be written as a product of two discontinuities of the lower point wave function coefficient, which is sort of remarkable because it really shows that the wave function actually factorizes when you take the discontinuity with respect to the internal lines. And the formula and the notion that they use for the discontinuity is just this formula. Okay, so if f minus a star, with respect to x, you are taking the discontinuity, which is why you are making the y with a minus sign and then subtracting the function from it with its complex conjugate and so on. Okay. And so now we have discussed like how the wave function coefficient factorizes. Now, once we know that wave function coefficient actually factorizes in terms of the lower order wave function coefficient, what can we do with it? So next it comes that the Melzer proposed something called the dispersion formula, which actually gives the full wave function coefficients from its discontinuity. Okay, so now as you know that the higher order wave function coefficients can be written in terms of the lower order wave function coefficients. So you put it there. because you really know the disk of psi 4 can be written off from this formula, disk of psi 3 and disk of psi 3. So you just put it here and complete the integral, then you know the full result. So you can really use the lower point wave function coefficients to cook up the higher point wave function coefficients. And very recently, 2024, Stefan Ezrin, Zitong, and Yuang Zhu, they showed that for a correlator, there is a similar sort of factorizations. And the notion of disk that they used is this. Okay, and this is the same discontinuity definition that I am also going to use in my work, and that I'll discuss in a minute. Okay, and then there is another paper called In-Out Formalism for In-In Correlators by Yaniv Donat and Enrico Payer, that there they also derived a cutting rule for an endpoint two-side correlator at any loop. So there are two bulk vertices, and within these two bulk vertices, there can be any number of loops. And for this loop, they showed that this type of formula exists using the largest time equations and the in-out formalism. Okay, so and they restricted their computation only for the conformally coupled scalar at IR convergent cases. Okay, so the interaction which are late time IR convergent. So for example, phi 4 onwards. Okay. So let me now tell you what we have done in our work. So we tried to see whether this correlator factorization can be understood from the Schwinger-Keldysh formalism. So as you know, in the Schwinger-Keldysh, if you restrict ourselves at the two bulk vertices, there can be four diagrams. So since for the general rule says if there are v number of vertices, there could be 2 to the power v number of diagrams and so on. So here there are four such diagrams. This GP++ says that it's a bulk to bulk propagator connecting two plus labeled vertices, and it's actually a Feynman propagator as defined in equation 11. So it's a time order propagator, and when both the vertices are minus, it's GP minus minus, and when it is plus and minus, they're connected by something called Whiteman function, and they can also be written in terms of the mode functions that we defined before. Okay, so the entire correlator can now be written as in equation 10. Okay, so there are actually four subdiagrams, and you have summed them up. Okay, and then you have to perform the eta integral and so on. So at least for the tree level, this is how it goes. Okay, now let us investigate how this analyticity property that Enrico, Harry, and their collaborators did in their optical theorem papers is required in this case of the bulk to boundary propagators of the Schwinger-Keldysh diagrams. Okay, so for the correlators, not for the wave function coefficient. So the bulk to boundary propagators for the correlator can be written in terms of the bulk to boundary propagators of the wave function coefficient in this way. Then just by applying the analyticity, it can be shown that kk plus is nothing but k minus k minus. So this kk plus actually means a bulk to boundary propagators connected to the plus labeled vertices, and kk minus says it's a bulk to boundary propagators connected with the minus labeled vertices. Okay, so now just by using the analyticity and Feldman largest time equation, which has inbuilt unitarity, leads to the following identity written in equation 13. So if you take the discontinuity of any bulk to bulk propagator, the answer is same. So this is what it says, the equation 13 says. So now if you take the discontinuity of the correlator, the discontinuity operation directly hits the bulk to bulk propagator, since you are taking the discontinuity with respect to the bulk to bulk momenta variable, and therefore it leads to this. So sigma can takes two values, plus and minus. So similarly, sigma 1 and sigma 2, both the actually takes two values. Now after doing some algebra, you can show that this part, which is eta 1 dependent, can be coupled with this guy, and eta 2 dependent part can be coupled with that guy, and therefore if you evaluate the integral, the result you obtain is just discontinuity of some contact level correlator. Similarly, the eta 2 part also gives rise discontinuity of a contact level correlator from the right edge. Okay, so therefore disk PB1 and disk PB1 appears. Now next come to the other line. So this KP minus minus of KP plus, this guy can be again coupled with this part, and similarly this eta 2 dependent part can be coupled with this guy, and evaluate the integral. And if you try to do it, you can see that it is not possible to write in terms of the correlator, but it can be write in terms of the imaginary part of the wave function coefficients. So that's how this B tilde appears. So in a minute, I'm going to show what is the structure of this B tilde. But let me now mention that for any R site 3-level correlator, this single cut discontinuity formula is valid. So here what it means that if I have a correlator with r number of bulk vertices, and if you cut the rightmost internal edge, the formula goes as this. Okay, and B tilde, what we call auxiliary objects, has this kind of form. So in equation 18, the first one, this p tilde 1, has imaginary part of the wave function coefficients. And if you compute the correlator, you'll see that correlator are always made of the real part of the wave function coefficients. If you remember, it's mod chi square. So if you take mod chi square of any exponential object, it really gives you the real part of these wave function coefficients. So now if you replace all the imaginary part from here by a real part of this wave function coefficients, you actually land to the correlator. So far we do not have yet a better understanding how to cook up this B tilde objects starting from the path integral formalism that actually helps us to compute these correlators. Okay, so this is something that we can look for. And this single cut rule actually works for any sort of derivative interactions and loop integrand as well. So it's important point to mention that it works for the loop integrand, which means the integrand of the momentum integrations, the three momentum integrations, because unless you have the support of the bulk to bulk lines, you cannot take the discontinuity that we define in our paper, because discontinuity really works only on the bulk to bulk line. So the momentum integrated in form, the answer will not have the access of the three momenta part. Okay, so that's why you cannot act this disk operation on the full result. So only thing that you can do is the integrand. So anyway, the integrand can be computed using this disk. Okay, the lower point disk and so on. So now let me just show you that once you have this kind of formula, this B2, disk of B2 in terms of disk of B1 and disk tilde of B tilde, you can use them in the dispersion relation and show that it can be the higher point correlator can be computed in terms of the lower point object. So you first compute in let's say in the conformally coupled phi cube theory, you compute the wave function coefficients, you take its real part and take its imaginary part, you compute B1 and B1 tilde, then take their discontinuity, and you land to equation 21. Similar thing can be done for any conformally coupled or massless scalar theory. And if you do this and put it here in equation 19, what you get is this. So the blue circle actually says that there is some disk B1, and red circle says there is some disk tilde B tilde, and you get this. If you sum them up, what you actually get is something called dressing rules, and derived by Chandramouli, Arthur, and their collaborators in a paper last year. Okay, and their computation was based on the shadow formalism in the Euclidean ADS. However, our method shows that even without going into this shadow formalism in the Euclidean ADS, you can cook up the same sort of dressing rule using the single cut rule successively. Say, for example, you want to do it for the three sides, then you have to cut the lines successively by applying disk twice, and then you use the dispersion formula, and you can lead to the dressing rules. Okay, so this is something that we have observed in our paper. So this is there can be various things that one can do with it. Like there is another way of understanding this cutting rules from the Enrico Pier's in-out formalism, because the formula that it discussed in his paper is not actually correct, because it fails to capture the phi to the power odd type of interactions correctly. If you check the formula that I showed previously, and if you take a, say, for example, conformally coupled phi 5 interaction, it actually fails. However, in our from our result, we actually see that this B tilde is the object which contributes to the phi 5 or any phi to the power odd interaction, and for phi to the power even interaction, B1 contributes. So it will be really nice to make the connection with this in-out formalism and correct the results that they wrote in the paper. And so by saying that, I will stop here and have a nice day, and thank you for listening to me.